What I'd like to talk about with you today is the symmetric interior penalty DG method for cycling. This is work that's done in collaboration with Elise Gabriel and Carsten Uphoff. And essentially, we are going to go through a couple of things. I'll outline the sort of problem setting and identify some of the modeling challenges associated with it. We'll briefly discuss finite element methods in a sort of continuous Galerkin setting and a discontinuous Galerkin setting. Then I'll discuss some of the specifics of this symmetric interior penalty method. And part of that discussion will be a sort of walkthrough of the derivation of the equations in the hope that this demystifies the nature of the method. And the reason I'd like to just spend a little bit of time dwell on those equations for a little bit is just because this method I think is fairly new to this community, and I think it needs a little demystifying. So we'll walk through that slowly. We'll discuss a little bit about the sort of reference implementation we'll be using in the context of the results that I'll show, called tandem. And then finally, I'll show you some time-independent examples of problems that are relevant to seismic cycling. These will be manufactured or analytic solutions, and they'll all be time-independent solutions. The time-dependent solutions will be shown in Elise's talk at 10 o'clock. Okay, so our problem setting is, well laid out by all the talks in the preceding days. So thanks to all the previous speakers for going through and explaining all this for me. I can skip a lot of the motivations and just focus on the sort of notational aspects of what I want to describe. So we're considering, elastic media indicated by this kind of brown region here with an embedded fracture, okay? And you'll see there's quite a bit of notation in the talk, so I just introduce some of the variables as they pop up. This gamma n will be referred to as our Neumann boundary condition, or places of the boundary where we have Neumann data, and gamma d will be places where we prescribe Dirichlet data, and n will be our unit normal, okay? So what we're interested in doing is developing methods that solve essentially this coupled problem of rate and state friction, as indicated up here, with an elastostatic problem. So linear elasticity, isotropic, constitutive relationship, independent, so no inertial terms here, okay? So no acceleration terms appearing in the conservation of momentum. And, to complement and close this system, we have our constitutive relationship here, our Dirichlet data, our Neumann data, so in this case a free surface, and we have these three special conditions that I'll just pause on and dwell on for a second. So the first is sort of fault constraint that describes that the jump in the displacement u will be given by some function or some quantity functional, let's say, called g of f, which is related to our slip and our friction law, so the coupling between the rate state friction and the elastic problem is coming in here with this jump condition. And then these two statements are basically, the sigma here is any little squiggly interface I might draw within my elastic medium away from the fault. What I require is that the jump and the displacement should be zero, and that the jump and the normal stress is zero. So I want continuity of the displacement and continuity of the normal stress along arbitrary interfaces within this gray region, okay? And if people aren't familiar with this notation, this double square brackets indicates the jump operator. Okay, so that's our problem statement. Fairly familiar, just with a little bit of extra notation for what I want to present. And in terms of modeling challenges for seismic cycling, it is complicated and it's hard from a simulation perspective, because the time scales of interest are wide. They live at a wide interval. The spatial scales that we want to resolve also live at a wide interval. The Earth is not purely homogeneous. So, non-constant material properties off fault is something we're interested in. As we saw in the structural complexity talks yesterday, natural faults rarely occur in isolation, and they're usually not planar. So you have networks of faults, not independent planar faults. And the displacement field is actually a solution to an elliptic PDE here. That's generally considered a somewhat more challenging problem to solve than, say, a pure hyperbolic problem. So it's elliptic. Okay, so DG methods, discontinuous Galerkin, or DG methods for elastostatics. Why? I guess that's the question. What is it, and why do we want to use this approach? So DG methods are finite element methods, they're volumetric methods, and since they're finite element type methods, they seek solutions at the weak form. So they're not solutions at the strong form or the original PD on the other page. They're a solution to a weaker problem. Finite element methods are nice because they support non-affine or curvilinear element geometries, and they support a wide range of mesh types and cell types. And I draw some pictures over here of the different types of meshes and cell types that you might use with finite element methods. So those are things that are desirable given our modeling challenges. And what's specific about the DG methods is the function spaces or the approximations we'll be making for the displacement in our case are defined element-wise, so they're non-conforming, and the regularity requirement is imposed weakly along cell faces via penalties. So this is a 1D example here, and what I'm talking about or mean is that where I have these sort of cells indicated by these blue dots, right? This is a cell, this is another cell. If I want continuity or a jump condition, I enforce those constraints weakly by integral expressions that occur and live on, defined on the faces. And so this is really useful for problems where the solution is smooth, because you can impose the regularity where you want the field to be continuous. And it's also useful for problems like the seismic cycling situations where you have an embedded fracture where you want to impose a jump, okay? And you can do that with a penalty as well. And that's that latter point that's very useful for DG formulate, using DG in the context of cycling. So I want to walk you through the weak forms and the derivation of the method. To do that, we're going to first consider, essentially what the weak form looks like for a single element K with a sort of outward pointing unit normal NK. And essentially all you do is you pick a test function, V, you multiply it by your strong form of the equation by V, you integrate by parts, and you'll get this expression, okay? So sort of grad of the test function contracted with the stress, and here is the surface integral term, the boundary integral term associated with the normal stress, okay? And that's, just for a single element. So very, very straightforward. And then we consider the case where you have two elements, Ka and Kb, that are stuck together and share a common edge E. And what you essentially have to do to derive these equations is consider the contributions that are coming from the two function spaces that are defined on Ka and Kb, and sum them together, okay? So that's what we're going to do. We're essentially going to think about the two-element problem with a shared edge and write out what that surface integral looks like. So you do that. Here's our sum. It's just the same surface integral from the previous side, but defined for, approximations on cell A and on cell B. If you add those together, you'll note that these normals, the outward pointing normals of the shared face, are actually only differing by a common sign. So one is the negative of the other. So you can combine those, use one normal. And then if you do a little bit of algebra and manipulate things, you can rewrite this expression to look like this, it's just algebra. There's nothing fancy done there. And ultimately, you can use this sort of compact notation, which expresses the discrete integral, or the integral of the problem in terms of, along that edge, in terms of jumps on the test function, and jumps of the normal stress, and averages of the normal stress, and averages of the test functions, okay? And you might remember, but I probably went through it too quickly, that this last term is actually zero because we really want continuity. It's part of our problem description. We have continuity of the normal stress, so those jumps are zero. And ultimately, we end up with these integrals that are just compactly written as jump of test function dotted with the average of the normal stress applied on the trial function U. Okay, now if you want to go and then take your two-element problem and write out the formulation for an entire mesh or an entire problem, okay? And we'll consider the case first without the fault. What you need to do is decompose the domain into a set of elements. Then you want to sum the weak form or the element integrals over the volumes and all the element contributions, the weak form contributions over the edges of the surfaces, okay? V will be our set of element volumes. S hat will be our set of edges. So when we do that sum, we have our volume term here, which looks pretty familiar. It's just the same as before for a single element, but now I put the implicit sum there and write the integral over V. And I have this term, which we just saw where it comes from. Okay, so that's our jump of test function dotted with the average of the normal stress. And we have our right-hand side term over here. So basically, I've just taken, on the previous slide, the two-element case, summed over all elements. And then, but you might note that none of our boundary data has yet entered the problem, okay? And the way we do that is we introduce two new terms. Well, actually, we add 0 to the right-hand side twice. And this basically, we add this blue term here, which is the so-called symmetrizing term. It's essentially this expression with the u and the v swapped, okay? And you add that to both sides of the equal sign, so you've added nothing. And you also introduce this other term in pink box here, which is basically penalizing the jumps between the test functions and the trial function. This parameter here, gamma, is known as the penalty. It's strictly greater than 0. And when you add these two terms together, this will lead ultimately to what we'll refer to as our symmetric interior penalty DG scheme. Okay, so I don't go through the details of why we actually want to add these terms, but I just show you how to do it and then how you get the boundary data in, and I'll summarize a little bit, a few more details about these terms that are added and what the consequences are. Okay, so we've done nothing. We've just added something, the same thing to the left and right hand side. Now, what we do is we split these integrals into two sets. Okay, so we take, instead of just looking at the integrals over all facets treated equally, we split them into interior facets and exterior facets, so facets that live on the boundary, Dirichlet data boundary, and interior facets which aren't connected with that, Dirichlet data. Split the integrals, and then we go and insert our boundary data. Okay, so our boundary data can be imposed here, right? That's from our continuity of the normals of the displacement. It should be 0. So these two terms are 0. And the terms that were here, let's flip back, right? This is our normal stress, and applied on the test function, on the trial function, dotted with our test function u. Well, we know what u is, right? It's on that Dirichlet data, it's given, right? It's GD, it's our constraint that we specify. So we insert a known Dirichlet data here into those two terms, okay? And everything else is left as is. So that's for the case where you don't have an embedded fault. Now we consider the case where you do, and let me just get rid of this box here. So in the case where you have a fault, you essentially follow the same procedure, except you introduce a new set of facets which are associated with the fault. So you have the same splitting of this symmetrizing term in the blue box. You consider interior facets that are not part of the fault, facets which are part of the Dirichlet boundary, and facets which are living on the fault. Okay, so the same thing, add the same term to both sides, express the integral into these, in terms of these three different regions or facet regions, and then insert our known data into the trial functions that appear the test functions which appear on the, trial functions which appear on the right-hand side. So as before, continuity of the displacement of fault, Dirichlet data here, and our slip constraint given by the friction law, rate and state friction GF, goes in here, okay? And with that, you actually have now modified the classical symmetric interior penalty DG scheme that's sort of expressed and written out in Beatrice Riviera's book, but now you've expressed it and included very easily and simply the embedded discontinuity arising from a fault. Okay, so it's quite straightforward to include the jump condition associated with the fault in the formulation. You just have to, basically break up the integral into one more set associated with the fault. Now the penalty terms here, they're used to enforce the boundary data, so associated with this constraint and this constraint, which is 0. The penalty itself needs to be greater than 0, and there's no upper limit on how large it should be. The larger gamma is, the better you will impose your data, your boundary data. However, the larger it is, the larger the, let's say, condition number or of your discrete operator is going to be, and that will be a problem, because we compute in finite precision arithmetic, and it also affects the potential of using iterative methods. So the larger the penalty is, the harder it is it's going to be for the iterative methods to converge. And so you need to choose the largest possible value of this guy, which does ensure stability of your scheme, but is not so large that it causes the solvers to struggle to converge. So we have a proof in the paper that defines a sort of lower bound on what lambda is. Sorry, I keep calling it the wrong thing, what gamma is. And it relates, it's a local penalty associated with the elastic Lamé parameters on cells that are adjacent to a given shared edge. And I'll show you some results later. It's not so large that the solvers have a hard time dealing with it. Okay, so we're not quite there yet. We've only derived the formula for, or the forms for elastostatic problems with an embedded crack. It's not quite a Sears or a seismic cycling framework yet. We need a couple of extra ingredients. So to just frame exactly what it is we're talking about with that method, I write out this slide to try and make the ideas concrete of what it means to use DG for these problems. So we described this already. We have domain partitioned into elements. We partition the facets into basically fault facets, so these red ones, or interior facets, or exterior ones, which are not shown here, okay? And then on each volume, cell volume, you introduce an approximation or a function space, so indicated by the black dots here. So we use a modal type basis. Each one of these black dots represents the location of our nodal basis function. And we do that on all volumes and on all faces which are connected to the fault. So these faces here, we introduce a new function space for representing quantities that are going to be defined on the face. So slip rate, shear stress, normal stress, those things are going to live on its own function space of the same polynomial degree as the function space used for displacement over each of these cell volumes. And the coupling is then going to require you to sort of project data from that you've computed from your cell, so like the stress or the normal stress, onto this particular basis function that's used to represent those quantities on the red interface. So that's part of the coupling. These dotted lines here are just meant to indicate that these basis functions actually are co-located in space. I've just drawn it in this expanded view to help clarify what the discontinuous nature of the approximation space. When we couple the displacement to the friction law, we use a special type of definition of the stress. We actually don't consider just the average of the stress. We consider the numerical flux, or the stress associated with the numerical flux in the DG formulation, which is the average of the stress across that face. And we include this penalization term, which is naturally there in the variational problem, but it's important to include. We don't have a theoretical explanation as to why that is. Sort of practical experience showed us it was necessary for stability of the time evolution of the problems with coupled with rate and state friction to use this form rather than just average stress. For the time integration, we use an explicit, an ODE formulation coupling the rate and state equations to the displacement, the PDE, and we integrate those with explicit, RK45 with the Dorman-Prince adaptive error, should say control, not code. So this is like ODE 45 from MATLAB. Okay, we take our discrete variational problem that you saw on the previous slide. We sort of pull out the bilinear form, which is all the terms that involve test and trial functions, and the linear form, which is just terms that involve the test function. We split those up, and we'll get and assemble those matrices that are associated with them, and you'll end up with the AX equals B or AU equals B problem. I put it in big there because it's important, and Brittany pointed out there are some people that spend their whole career just dealing with AX equals B. I'm one of those people, so it's a good problem for me to work on for that reason, because it's really important, right? The efficiency of that solve is basically the limiting barrier to time to solution or time to science, if you want to think that way. So for example, each time step requires multiple solves and AX equals B problem, right? If you do a multi-step explicit rubber cutter scheme, you're going to have to perform a series of solves. Cycle simulation may require 10 to the 6 or more time steps. That's a whole lot of solves that you're going to have to do. And if you like to use the discrete Green's function approach, you're going to have to perform one of these AX equals B type solves for every basis function that's associated with the fault. And there might be many of those. So you might end up doing a large number of solves just to compute all those Green's functions. But there's some hope that, we might be able to make progress, because the formulation that we use, at least, all the terms on the right-hand side consist of body forces, and all the boundary data and the fault boundary data and the Neumann data, okay? And that means A is constant in time. It's independent of time. We're doing many solves with a constant operator, many right-hand sides solves with a constant operator, so maybe sparse direct is a good option in 2D. Operator A comes from an elliptic PDE. Our SIPG scheme gives us a symmetric positive definite system, so there's some hope we might be able to use multi-level preconditioners like multigrid, and also maybe using block Krylov methods and exploiting some recycling and deflation ideas to accelerate the solves. So we use in our models a multi-grid type method. It's optimal in the sense that the complexity is scales like O of n, or it is O of n. We use a particular variant where we can consider both coarsening the polynomial function space from whatever P4, say, down to P1. And then we take that low order problem and we coarsen it further using algebraic multigrid. This is fairly standard, works well. It works for continuous Galerkin, works for high order DG discretizations, and it works well for cycling, even when you include a fault in the problem description. The convergence is almost independent of the existence of a fault or not. We put all these things together and have implemented this in a piece of software we call Tandem. Tandem supports a number of things which we list here. So it's 2D and 3D spatial discretization using structured meshes of triangles and tets, high order curvilinear representation of the geometry. We do that or enable that through the GMSH functionality and the mesh representation that GMSH gives you for high order elements. We allow for interior element representations of material properties. We have efficient kernels for the assembly and the sparse matrix vector products for the DG kernels using a library that Carsten developed called Yateto. It's a fully parallel implementation. So everything from loading the mesh, writing the output, running the simulations, that's all done in parallel. We use PETSI, so the Portable Extensible Toolkit for Scientific Computing, to give us the sort of linear algebra backend. And we also have this option to compute discrete Green's functions. The code basically, gives us good results, high performance results on single compute nodes with or without GPUs and large scale HPC architecture. Okay, in the last part of the talk, I just want to go through some tests that we've done to kind of convince you about the accuracy or the relevance of the method for cycling type simulations. So we consider some 2D experiments where we look at the effect and are we able to converge under mesh refinement and polynomial refinement for domains defined with that can't be described by affine geometries. Okay, so this is a circle with a circular hole cut in it. We represent that circular geometry with high order polynomials, and we solve an elastic problem. There's no fault at this point. Okay, and what's shown here are basically the L2 and H1 error norms. So L2 and H1 here, H1 semi-norm. And we're showing on each of these lines, colored lines, represents the solution sequence, the solution defined on a sequence of different meshes with different polynomial order. So black is P1, so linear shape basis functions. And the pink line here is state, so 8th degree polynomials. And what you see is the slope of those lines is consistent with the a priori error estimate. Okay, so you see basically constant values up to machine precision for the different function spaces. So that checks out. However, if you try and do this with affine meshes, so don't use the curvilinear representation, but just consider triangles with straight line segments, you go and reduce down to a second order or a first order method, depending on the norm you're using, independent of the polynomial order. And that's consistent. It does indicate why high order is good. Why high order geometry is a useful thing. We do the same thing for 3D cases. So it's a sphere with a spherical hole. We see the same type of convergence behavior. The slope of these lines increases as you go from low order n equals 1 to high order n equals 6 in this case. And the slope of those lines is consistent with what we expect from the a priori error estimates. Again, convergence kind of breaks down at around machine precision, so somewhere between 10 to the minus 10, 10 to the minus 12. That's expected. That's consequence of double precision arithmetic. To demonstrate maybe the benefits of using a sub-element representation of material properties here. We have a simple case where we consider Lamé parameters that vary in space with this kind of sinusoidal type pattern that's shown here. We represent those material parameters with a high order basis function. So a high order polynomial, same polynomial order that's used for the displacement field. And we again perform, in this case, a manufactured solution showing the convergence here. Again, we obtain the optimal rates, in L2 and H1 for spatially varying material properties and affine geometries. Okay, the last test we consider it's the first test we do when we have a embedded crack or discontinuity in the displacement field. And what's nice about this test is there's a parameter in it that allows us to control and define the regularity of the solution. And so we can make the problem, the analytic solution, have low regularity for which we don't expect high order convergence. And we can change that value of the parameter to be large, the gamma here, and that gives us a high regularity solution, which does enable convergence under polynomial refinement. And so we see for low regularity, we sort of converge at around order half in L2, sorry, half in the H1 semi-norm. And when you change the regularity to make it nice and smooth, then indeed, you obtain the normal a priori error estimates. Everything matches with the theory so far, which is good. Okay, so we switch now to some examples which are not analytic and not manufactured. These are they're still independent of time, and they're leading more towards that scenario that might be relevant for Sears type application. So here what we consider is a 3D problem. We take the sort of Ridgecrest fault system or some idealization of the Ridgecrest fault system, and we impose slip on those fault segments that are indicated up here. Okay, I chose them by hand. So I prescribe the slip, and I compute the displacement based on that prescribed slip. So this is an instantaneous solution. It's independent of time. There's no friction law in this. It's purely kinematic, okay? This is the zoom in of the mesh, what it looks like. We, again, use this high order representation geometry. This particular problem, it has, 400,000 tetrahedra in it. And to give you some idea of the run times for the P2, so degree 2 polynomial case, we end up with around 12 million degrees of freedom for the displacement. We could solve that on, say, 48 ranks on modest compute resource in around 90 seconds. And if we bump up the polynomial order to degree 3, we have something like 25 million DOFs. Solve on 48 ranks, we get an answer around 170 seconds. So if people like numbers, this is equivalent to, say, 130,000 degrees of freedom per second in the P2 case and 150,000 degrees of freedom per second in the P3 case. Okay. So here's some just snapshots of what the fields look like. For the displacement, we see due to our imposed slip, and it was a strike slip, prescribed with a strike slip setting, then we indeed have nicely discontinuous looking values for the displacement in the horizontal direction. But due to the fact that it's purely strike slip imposed slip on these models, we don't see anything discontinuous in the vertical displacement field. So in the eyeball norm, it looks great. When you look at the gradients of the displacement, you see fairly large artifacts when you use low order meshes, so low order geometry representations and low order function space. So that's what these panels show here. So this is the gradient of the displacement field as a proxy for what the stress might look like. Okay, and what we're interested in are whether there are discontinuities in the solution that are unphysical and are associated with numerical choices like how the geometry is represented. So when you switch to using a high order, what I call P3, P2, this is P3 for the displacement, so degree 3 polynomial for displacement and degree 2 polynomial for the geometry, all those artifacts and aberrations that you might see along the fault edges, say here, are completely gone because there are no, if you like, kinks in the fault due to the geometric representation and numerical model. So it's intrinsically smooth, and as a result, there's no places where the stress artificially localizes. There's no kinks in the fault itself. So you get nice smooth solutions, particularly in the vertical displacement. Gradients in the vertical direction at least. So the last two examples are sort of extending that a little bit. And here what we do is consider some simple 2D models where instead of imposing the slip on the fault, we just use a slip law, a very simple slip law, a friction law where the friction is constant, the normal stress is constant or independent of slip or slip rate, maybe depth dependent. And we impose that along this interface and impose convergence. So this is a bit like a megathrust setting. Okay, so this is one step beyond the purely kinematic models where we drive everything with slip on the fault. Here we just impose the Dirichlet data and prescribe a simple friction law. And so what we show here are basically the solutions you get for this very simple geometry using affine meshes, so edges, triangle mesh edges that have straight line segments, versus curvilinear. And what you can see, these have the same color scale range as the, again, even in that case of simple friction law with straight line segments and your fault, you have a whole series of stress concentrations appearing along this interface just due to the nature of the geometric representation. But if you switch to a curvilinear approach, this doesn't happen. Everything's nice and smooth, and your friction law, if it was time dependent, maybe coupled to rate and state, would be better behaved. That's kind of the point. The last example is a little bit more complicated. Here we don't bother worrying about curvature, geometric representation of curved objects. We just use straight line segments. We have similar sort of megathrust type setting in which we also introduced three little splay faults. We apply the same type of kinematic friction model, which just to simplify the analysis and make it independent of time, we do the same thing. And what you see here are computed displacement solutions and gradients of the displacement in the top and the bottom panels respectively. And I guess the only thing I want to highlight here is this displacement field is fine, but because of the sort of incompatibility that occurs where your splay intersects this main thrust, you will still generate singularities here in the gradient field, which is again, as I said, a proxy for stress. But these are not due to numerical artifacts, right? These are physical. These are consistent with what you would expect given the geometry of these intersecting faults associated with display and the main thrust. So they're still there in the numerics, but they're physical in this case, and not arising due to numerical approximations. So in summary, I think we've gone through the DG formulation for sears. We talked about symmetric interior penalty methods, and we showed some examples that illustrate that it is yielding high order convergence in space for different types of problems with and without faults. We've given you some examples of how the curvilinear representation of geometry is useful, and what the consequences of not using a high order representation of geometry are in the context of curved faults, and in particular how that manifests itself into the displacement gradient, also gradient of the displacement field, i.e. stress. We talked a little bit about our reference implementation tandem. Tandem's designed for sears or cycling models, cycling simulations, and for modern HPC infrastructure. It addresses these sort of computational demands by using efficient libraries for the kernels associated with the DG formulation, the linear algebra, the solvers, and the preconditioner. The implementation has a nice geometric multigrid, hybrid algebraic geometric multigrid preconditioner, and that's pretty insensitive to the presence of a fault or not. And it also allows this option for using computing discrete Green's functions. And just as a reference to anyone who wanted to see some sears experiments, at least it's going to talk about those time-dependent models at 10 o'clock. Thank you for your attention.